So I'll dive right in. Like I said, this is only going to be 3 questions. I don't expect to take much more than half an hour, hopefully. As always, if there's any questions or anything that's unclear, please let me know in the chat. I'm really good at keeping an eye on it, but if you do put something there, I'll get to it as soon as I spot it. Okay, so the first question is on the screen here. A beam of yellow light from a sodium vapor lamp is incident on a diffraction grating. With 890 lines per millimeter, we're told that the light is not monochromatic, which the explanation that follows tells us that means it contains 2 slightly different wavelengths. So there's one that's 589.0 nanometers, that's the width of the light, a lot smaller than some of the waves and their wavelengths that we've been talking about in previous weeks. The other wavelength in this light is 589.6 nanometers, so just slightly different, but different enough that it matters. The question we are asked is how far apart is the first order maximum for the 589.0 nanometer wavelength light from the third order maxima from the 589.6 nanometer light when they're illuminated on a detector screen that's 3.11 meters away from the diffraction grating. So what's going on here is we have a diffraction grating. It's basically a bunch of little, there's no way for me to draw this really accurately, but a bunch of different grating lines. We can illuminate it with light, and imagine that we just kind of pick some, doesn't have to be a central point, because it's repeating, the grating kind of is very large relative to the distance between the individual gratings. But anyways, what you can find is if you have a detector screen over here, there will be kind of bright spots, which I'm not drawing so well. It follows all the same physics and same geometry as interference from waves that we've looked at before. So you can imagine that there's, from the central point here, there's different interference orders. So you have kind of the 0th central, no interference at this here, but then you have the first, second order, and so on. It would kind of keep going down and up because it's the whole pattern is symmetric. Something like this. We could also, maybe I'll switch colors really briefly. We'll just label the screen. We'll come back to this in a second. Put the distance from kind of the grating to the screen. I'm going to call that L. And the distance that is between, on the screen here, or the detector, between the different fringes, or the kind of the height from 0, we're going to call this Y. And you can kind of see already, my drawings are never that great, but kind of this L is kind of the bottom of the triangle, Y is the vertical side, and it kind of picks up this angle theta here. If we chose the m=2 spot, we'd have a different triangle, but the same concepts all apply. Okay, so that's kind of the picture, it's an idea of what we're working with. This is an interference problem. And pretty much every interference problem, as we talked about last week, you're comparing kind of, or you have light that goes on 2 different paths. There's a path difference. And if that path difference ends up being a integer multiple of the wavelength, you get constructive interference. It's basically every interference problem in a nutshell. For problems with geometries like these, our path length difference was d sine theta. That's the derivation that's in the notes. And to say that that's equal, we're looking for constructive interference. That's equal to m lambda. So that's an integer multiple of the number of wavelengths. And the reason that we're using constructive interference is because we're looking for the distance between 2 different maximums. And maximums in intensity or whatever, it's the same as saying constructive interference. So we don't actually have this angle theta here for either of the maxima that we're looking for. But what we do have is the distance to the screen L. And what we're looking for is the difference in position along the screen. So that's kind of like the Y's. So what we need to do is we need to try and get rid of the sine theta with something that relates the Y, the L. kind of the parameters we have. So I think this is something that should be in the lecture notes, but it's pretty straightforward to derive, and I think it's useful to understand and see repeatedly. So I'm just going to quickly do it here. So what we have right now is sine theta. You guys may be familiar, I hope you're familiar with the fact that tan theta is equal to sine theta over cosine theta, or in other words, sine theta is equal to cosine theta multiplied by tan theta. So the angles are really, really small, which they typically are in most of these problems, and they need to be for us to solve them, so it's kind of almost a guarantee when you're solving these problems that you're in the small angle limit and you can make an angle approximation. Cosine is always equal to 1, or it's approximately equal to 1. It's super close to 1. So what we say is that sine theta is almost equal to tangent, because that cosine we had in the previous line, that's equal to 1, tan theta. If you remember the trigonometric ratio, tan, when you have a triangle, tangent is the ratio of the opposite side to the adjacent side. So in our case, with the triangle I put above, that's y over L. So where we have sine theta, we can sub in y over L. And we're basically just relying on a small angle approximation. And what we want to solve for is we're looking for the difference between two positions on the detector screen. So the positions are going to be in terms of y, so I'll just solve for y. So we have y being equal to ml lambda over d, and I'm going to consider this to be our master equation. But you can imagine that we'd have two, right? We're looking for the first order maximum for the 589. Let's call that the first wavelength, so it's the first one we're given. So the position of that maximum, we'll call that y1. It's the first order, but we won't fill it in. We'll just call it m1, the interference order for the first wavelength. I'm going to multiply that by lambda 1, that's the wavelength. And then off to the side, I'll put L over D. And I'm putting these off to the side because they're constant whether we're looking at lambda 1 or lambda 2. And we also have the same thing with different subscripts for the second wavelength. And the only real difference, we'll put a different number in for lambda in either of these, and we'll put a different number in for m. So for the first one, we have a first order map we're looking for, and for the second one, third order. So m2 is 3, m1 is 1. The end result we want from the problem is actually the difference between these two quantities. So I think hopefully it's pretty obvious if m2 is 3 and m1 is 1. And also if you look here, lambda 2 is a little bit bigger, 589.6, a little bit bigger than 89.0. So y2 is going to end up being bigger, so I'm putting it first. So this whole delta y comes out positive. You could do it the other way, it would come out negative, and you would just kind of have to use your common sense to realize that you want a positive number, because we're just at a distance. Okay. So let's fill in what we had above, m2 lambda 2, L over D minus m1 L over D. We can factor this a little bit. They both have L over D. We have m2 lambda 2 minus m1 lambda 1. And I think this is about as far as we can take it in terms of variables. So at this point, we're ready to plug some stuff in. One thing that I think is not challenging, but just an adjustment, the ones you've previously been working with. Most waves in musical instruments, water tanks, that kind of stuff, the wavelengths are units that you're familiar with, millimeters, centimeters, meters. The lengths are all units you're familiar with. Nanometers are quite a bit smaller. So you just need to remember that 1 nanometer is equal to 10 to the minus 9 meters. Nano means 10 to the minus 9 for metric prefixes. So what I'm going to do to make everything convenient is on the fly, I'm just going to convert everything to meters. So our screen is 3.11 meters from the grating. Deal with D. What is D? D is the width of a grating. So what we have is we were told that there are 890 lines in a single millimeter. So what that means is that the size of a slit or a single grating is determined by taking that 1 millimeter and dividing it up into 890 pieces. So you're taking the reciprocal of this. So to really quickly get this into meters, I'm just going to add a conversion. So in 1 meter, there's 1,000 millimeters. Meters crossed off. And this looks something like 1 over 890 times 10^3. And the units on that is meters. I'm just going to leave this bit here as is. It doesn't matter. We're always going to chuck everything into a calculator in a second. So having kind of a gnarly looking fraction doesn't really hold us back much. Okay, so that's D that we just filled in. And the interference order, we're looking for the third maximum, so I put a 3 in. That was for the 589 nanometer wavelength, or 589.6, excuse me. We want this in units of meters just so we can do simple calculations in our calculator. So all we have to do is chuck a 10 to the minus 9 on there and assign it units of meters. The interference order on first wavelength is 1, so I haven't even written that down because multiplication by 1 is, you don't need to write it down. That's everything. So that's, at this point, just plug into the calculator and hopefully don't make any mistakes. What I think you should get is something like 3.27 meters thereabouts. So it tells you that the third order and the first order fringes are really far apart. Now, one thing you guys should always do is ask yourself if this kind of answer makes sense. And I'm going to tell you that because we had to come up with this question and we didn't really check it before coming through it, it actually doesn't make sense. What this says is there's kind of a big distance, like 3 meters here, and the screen is 3 meters here. So the triangle that we kind of like triangle here that involves theta looks something like this. So the reason I'm saying this doesn't make very much sense in this case is that theta is very large. This is like a 45-degree angle. That's huge. So the small angle approximation wouldn't actually apply here, but that's just because we put together a bad question. So the physics here is still good, but it's just if you guys, it's always good to kind of build up your ability to check these things. So if any of you think of this and notice this and think it's a bit strange, well, you're correct. It is a bit strange. It's just because we were a bit sloppy putting these questions together. Okay, question 2. Pretty similar setup. I'm exact same kind of experimental and physics and all that kind of stuff. So we expect used by a planetary atmosphere. So what this is, we have a diffraction grating like we had here, kind of the same setup. So I'm not going to draw it again. And the word spectrometer means kind of just you can do analysis to figure out what's in things. So if you, this grating spectrometer, we're using to look at a planetary atmosphere and actually figure out what is the composition of the atmosphere. So this grating is different than the previous one. We're told it has 50 lines per centimeter. The detector is 15 centimeters away. And we've been told that there are first order fringes. There's a big collection. And they're at these, what do we have? 1, 2, 4, 5 distances that are shown here. So we have 5 kind of unique patterns in the first order fringes positions as shown on the detector. So we're asked to find the composition of the atmosphere, and what we're going to do is we're going to use the table provided that tells you what the wavelength of different gases are that might make up the atmosphere. We're going to compare them to the wavelengths that we calculate based on the distances provided. So what I'm going to do is I think I will take this equation here from the previous one. Like I said, the setup and the fit are all the same. so I'm not going to go over it twice. So we had d y over L is equal to m lambda. I'm not even going to write the m because m is equal to 1 because we're told that every single one is a distance associated with a first order fringe. So I'm just going to say lambda because m should be in front of lambda, but it's 1. So unlike lambda, let's wait, or let's figure out what d is before we get too deep into the question. So we're told that we have 50 lines per centimeter. And the way that I do this, you guys can do it differently if you have a better way. It's just, I find it's very simple and well out. If you have a different way of figuring out what you think the individual grading size is that makes sense to you, go ahead with that one. But if there's 50 lines in 1 centimeter, then in 1 centimeter, how big is each of the gradings? We have to take that centimeter and divide it up into 50 pieces. We want that in meters. So you just multiply a simple conversion, unit conversion factor. So there's 100 centimeters in 1 meter. The centimeters cross out. And what we're left with is that d is equal to 1 over 5,000. And that's in units of meters. And we could even simplify this a bit further. Imagine you 1 over 5,000 is the same as 2 over 10,000, which we can really write as 2 times 10 to the minus 4 meters. That's a pretty nice, simple form for d. So that's the size of one of our one of the individual spaces on the grading. Okay, so what we're going to do now, we have d. We can just keep note of things down here. L is equal to 0.5 meters. With 50 centimeters, so that's half a meter. And the lambdas have been provided, they're in centimeters, so we're going to, on the fly, we're going to want to convert those to meters, but I think otherwise we're set. And we do want to calculate wavelength because we're comparing to the values in the right column of this table, so I think we're all set. We just have to do this 5 different times. So the first one, we'll just kind of go from highest to lowest. The first position that we're given, we'll calculate the wavelength. So d was 2 times 10 to the minus 4 meters. Y, it was 1.075. To convert that to meters, there's 100 centimeters in a meter, so we just put 10 to the minus 2. And we want to divide that by half a meter, because that's our distance from the grading to the detector. And what you get, if you plug this into your calculator, make no mistakes, you'll get 4.3 times 10 to the minus 6 meters. And this is another unit that we have to learn or become familiar with. I guess you guys probably already know it, but just becoming familiar. Previous question, 10 to the minus 9, I think we put this somewhere. Yeah, 10 to the minus 9 meters, that's a nanometer. 1 micrometer is equal to 10 to the minus 6 meters. So this table, notice it's in units of micrometers. So we can convert if we really want to. It's 4.3 micrometers. The conversion is obviously very simple when we have things written with a proper 10 to the minus 6 there. Okay, so that's all we need for the first one. We could even, let's refer to our table and denote that we found this one already. Not to be confused with this one. We did not find this one. But this just illustrates that kind of calculating this with enough precision is important. Okay, so the next one is 1.9 centimeters. We set everything, it's the exact same formula. If you guys are doing this to check the answers like you're doing it at home, it might even be, what is this, 2 times 10 to the minus 4 divided by 0.5, because you'll use that every single time. You could perhaps save a bit of effort. So if you guys plug this one into your calculator, you will get out, I'll do the conversion to micrometers right away. you'll get 7.6 micrometers. So since everything's the same and you can see the pattern already, right? This is where we put the first number in, this is where we put the second number in. I'm just going to go through the remaining ones and spare you guys the boredom of me filling in the answers that you know are kind of the numbers that you know are coming and have already seen before. So when y is 2.35 centimeters, we get 9.4. Let's keep track of what we're finding. So we found this, we found this. When y is equal to 2.6 centimeters, we find that lambda is equal to 10.4 micrometers. And just a reminder, again, if you're doing this on your calculator, you will get these coming out as 10 to the minus 6, and I'm just doing the conversion as I'm writing it down here. So the last one was 3.75 centimeters, and the wavelength we get out of that is 15 micrometers. So these ones, so basically we found all the characteristic wavelengths that are associated with carbon dioxide, and we found the only one that's associated with CH4, which is methane. So that's the composition of this atmosphere that was measured by this spacecraft looking at a planet, that kind of thing. Okay, so this is the last question. Question more on reflection, and it's mostly just geometry, to be completely honest. If there are any questions before the end of this, maybe you guys can think of them and put them in the chat. Otherwise, I think we'll be wrapping up pretty quickly. Okay, so we have an ant, and it's positioned. This is a bit strange, but we'll draw it and it will become clear. It's positioned between a mirror that's about 40 centimeters tall and a tree. So there's a tree on one side, a mirror on the other. The ant looks towards the mirror, and when it does, the image of the tree just fills the height of the mirror. We're told that the ant is 1.75 meters from the mirror, and we're told that the tree is 16.4 meters from the mirror. The question wants to know how tall is the tree, and even if it wasn't asked for here, we would definitely be making a diagram. This is kind of confusing, but will become very clear when we draw it out. So these are geometries that are probably best suited by straight lines. Okay, so I think we'll draw a horizontal line for the ground, like this, fairly horizontal. I'm going to put the tree on the left side. I'm just going to use a vertical straight line, and I'm going to put the mirror on the right side. So this is kind of the basic setup. You can imagine that we have the ant kind of somewhere over here. And based on this, let's switch to blue again. We can label kind of the geometry that we have, or the distances. So I'm going to call this is the distance from, here, let's just make it clear in case this is the mirror on this side, I'm leaving lots of space so we can draw. This is the tree. And right here is the ant. Okay, so the distance from the ant to the mirror, we were told, is 1.75 meters. I'm going to call this lowercase l for kind of manipulating equations. And we've been given the height of the mirror, it's 0.38 meters. I'm going to call this distance lowercase h. We've been given the distance from the tree to the mirror as well. So that's this distance here. I call that capital L. What we want to know is how tall is the tree. That's this distance here, and that'll be capital H. So those are kind of the quantities that we have. The key thing, and this is a bit of a connection to make, I don't think it's super duper obvious, but is where we're told that the image of the tree just fills the height of the mirror. So what this means, and this is just pretty much geometry, but some of the basic reflection stuff is just geometry. So you can imagine the sight line, this is the ant, it's super tiny. The tree fills the entire mirror. So what that means is let's trace out a light ray that goes from the ant's eyes to the top of the mirror. And we know that the image of the tree fills to the top of the mirror, so there has to be another light ray that is reflected and goes to the top of the tree. Something like that. And if this isn't a convincing enough tree, you can do something like this, right? But the red path is a ray, a light ray, that's reflected off this mirror. I tried to draw it as best as I can, but obviously, as you guys have probably learned, not hopefully learned, but probably learned, my drawings aren't fantastic, but this angle in here matches this angle in here. This dashed line is horizontal. The black line here that defines the base where the ground is also horizontal. So basically what this means is if this angle is theta, this angle is also theta, and this angle is also theta. So the two on the top here, they're, and these two are theta just kind of by geometry. You can pick out a bit of a Z pattern, and the interior angles on a Z are equal. So this is all well and good, but it doesn't seem like it exactly helps us. But what we can realize, and it's kind of just a geometric argument, if these angles theta are equal, what we can imagine is this smaller triangle here, I'll try and trace over it tidily. We can kind of flip this over to the right, and we're not changing the geometry or anything like that. We're just kind of orienting it a bit differently. And then you can see that we have a similar triangle setup. Triangle that we flipped over, it has this distance L, this height here is still H. So basically we have, make them a little smaller over here, we have this tiny triangle like this, it has a right angle and an angle theta. And then we have this bigger triangle, also has an angle theta, H, big L. So if you have three angles that are similar, which these do, the theta, there's 90, and then there's whatever 90 minus theta is. There's a theta, 90 minus theta. If they have three same angles, then these are similar triangles. If these are similar triangles, then the ratios of the sides are equal. So what that means is we can write that H, capital H divided by capital L is equal to, oh, I messed up a little bit. Did anyone in the chat catch my error? No one in the chat caught my error. I guess that's good for me, but embarrassing for you guys. The distance capital L gets us from the tree to the mirror, but now this kind of longer triangle that we've drawn out, we need lowercase l as capital L. So I think with that fixed, we can set up the correct equations. So this is the ratio of the vertical side to the horizontal side for the big triangle. This is the ratio of same sides, corresponding sides for the small triangle. We have big L, we have little l, we have little h. We just need to solve for big H. So I'll just simplify this fraction a tiny bit, just to reduce kind of the number of calculations we need to do. But this is, I think, the equation is our final answer in variables. We just need to fill all this in and put it into a calculator. So the lowercase h, that was the height of the mirror. That was 38 centimeters or 0.8 meters. Capital L was the length of the tree to the mirror. That's 16.4 meters. And lowercase l was the distance of the ant to the mirror, so that's 1.75 meters. So I believe we put that into our calculator, we will get 3.11 is I think what I have written down here. It's a 3-meter tree, pretty typical tree height. Sounds reasonable, units all work out, so I'm pretty happy with that. I did not get a single chat message, so kind of lonely here, but hopefully that just means you guys found these questions were simple. John got 3.94. I totally believe that. I jotted the answers down in my handwriting. It's not super duper clear, so this will be recorded, so there's no way to hide. But yeah, if I got it wrong, then okay. So we have 2 people that are claiming it's my answer's wrong, so that's fine. But I think everyone would probably agree that we said it right. Just my calculator work got a little bit sloppy, which is why every time I say put this into your calculator, assuming there are no mistakes with the calculator work is always kind of important. Yeah, so I think that's all I have for you guys tonight. Totally happy to take any questions, but so John was asking how, for the first one, how can I show if we can find the angle theta? Let's go back to the first one. So I wish I had a bit more space. So I opted out of angles because we had this distance here and we were concerned with this quantity here. So that would be actually that challenging. But it is a bit unnecessary. So if you did want to find out what the angle theta was, I think that's what let me double check your question. How do you find the angle? Yeah, okay. So what you would do, yeah, so what I did is I used the small angle approximation to relate sine theta to some of the physical, like the geometric, so L and Y. Maybe I'm misinterpreting your question a little bit, but it will show me how you find the angle for the third order maximum. I mean, so I think, yeah, I think there might be a tiny amount of me not understanding what you're asking. Oh, yeah, using only that. Yeah, so one way you could do it, I suppose, which is more complicated, but maybe a little more accurate, you have d sine theta equals m lambda, but you know what, do we know what y and l are? I don't know if we can do it with that. What I was going to say is if we have this triangle, we have y and l, so what we can do is we can figure out that tan theta is equal to y over L. From that, you can say that theta is equal to the arctan of y over L. So you have theta here. You could take this whole thing, and if you wanted to, you could stuff it in there. But I think that would really complicate things, and it would get kind of, if what you were really trying to get at was this y, which is what we were trying to get at, it would be a total nightmare, I think. Oh, you were, okay, yeah, I see what you're saying. Yeah, so there are certain situations where when theta is small, so you can say that sine theta is equal to theta. And I think most of the decision making on when you want to use that or when you want to use what I detailed kind of on the right is in the context of the problem. So if you're looking to solve for theta and you're not even given L, that would be when you want to use that kind of process. for them, I think it's the decision making when you're trying to decide how to solve the problem is kind of highlighted in what I drew in red here. We knew we were going to look for something like this, and we knew we has L. So immediately, like when you have Y and you have L, you should immediately be thinking like, how can I work tan into this thing? The other thing to keep in mind with what you said, where you were talking about the approximation that um, sine theta is approximately equal to theta. This is only true if theta is in units of radians. So if you ever want to try and use that one, or you think you have a problem where that's applicable, you got to be working in radians. So I think in situations like this one, I think sticking to this approximation, that seems quite well laid out, right? I mean, it's just kind of begging you to use tangent here, parameters that are given. So yeah, I don't know if that exactly answers your question. I think the attempt to make approximation theta is equal to theta doesn't really it doesn't really net you much. So you're saying if you put, yeah, so what you might be running into the issue is that, like I said, this problem was slightly poorly designed. So you're probably going to take the inverse sine of something bigger than one, would be my guess. And you also have to be making sure that your lambda and your d, it's all in the correct units and all that kind of stuff, which is totally fine. It probably could be. Um, I get my error since can't have pi over 2. Mm, yes, pi over 2 does not play nicely into arcsine. Yeah, not sure if that is satisfactory. I'm not even. I think I've clearly kind of stated my case for why I think the way I did was sensible at the very least. Hopefully that's reasonably satisfactory, or